Alright, welcome back to the graphs slides. We're going to finish them up today and actually learn a bit of graph algorithms now that we know how to represent graphs inside of our computer, either using an adjacency list or an adjacency matrix. So let's get right on into it. I'd like to talk about traversals. This is very similar to the tree traversals that you learned in CSCI 41. So you have a graph somehow, and you likely want to go everywhere. You want to visit every vertex, most likely, or like you have some starting point and some ending point, and you want to search for how to get there, for example. My best idea of this is you have a maze. Like, this maze can totally be translated to a graph. Let me show you how. And if you were to do a traversal to visit every element, every vertex in this matrix, which is just a maze, or sorry, not matrix, in every vertex in this graph, then you would be able to find, like maybe from a starting point to an ending point, the A path or perhaps the shortest path. So let me show you how this all works out. So let me move this a little closer. But any maze, for example, can be translated into a graph. Watch. This is a spot where you could go. This is a spot where you could go. This is a spot where you could go. This is a spot where you can go, and you could go like this, right? And these are your options. Like from here, you could go up or right. From here, you can go down or right. You see how that's going to work out? And so you could traverse every vertex in a certain way. You could visit everybody, and eventually, like, you might hit some dead ends, of course. Like, you might start going this way when you shouldn't have. But assuming, like, you have a fast computer, you can try everybody really quick, and like you'll notice, like, all right, maybe we shouldn't go down there, but we could go up here, and so on and so forth, and you'd end up making it to the exit in time. Like maybe you go into this corner, but this is how the graph would look that represents this maze. You see it? Just from every center point of every spot that you could be in, they're all just little squares, right? Where could you go? Where could you move? And so this is a little bit of that graph. I think you could make the rest. But if we could visit everywhere, we could find maybe a path from start to end, or maybe we're just interested in a path or the shortest path. So that's the cool new thing. That's graph traversals. All right, so I'm going to show you the algorithms, and traversals, believe it or not, they create trees from graphs. And so we're going to come back in the trees chapter, which is right after this one, and talk about the theory behind it all, but I just want to show you all the algorithms, right? So the first one is called depth-first search. It's essentially a recursive algorithm, but we'll use an explicit stack here. But here's the concept. In a depth-first search of a graph, you have some starting place, and you want to visit everywhere. You want to go as far as you can, as deep as you can into the graph first. All right, so go as far as possible without having to retrace your steps. That's what the algorithm does, and it's going to visit everybody that's connected. Okay, it's going to take this amount of time, and we'll talk about that after I give you an example. But here is the algorithm: depth first search on some graph from some starting vertex. It's going to search through the graph for every place that's reachable from the starting vertex, and it's going to do it in a depth-first way. It's going to go as deep as possible into the graph without having to retrace its steps. All right? So this will make sense as I do the example, I promise. But here is the idea I'm going to use. We're going to use a stack data structure. And so this could be a recursive algorithm if we wanted it to be. But I'm going to draw it like this, I think, like a stack. I'll just draw it as a list because I have to draw it down here. So when I draw a stack like this, A, B, C, I want you to think of it as A's on the bottom, then B, then C. Right? So that's going to be the algorithm. So let's pretend we're calling our DFS function on this graph with a starting vertex of A. We'd like to search from A everywhere. Okay? So at the beginning, our visited set, it's all the places that we eventually want to go, it's empty. We start out an empty visited set. And we also start out a stack that's empty. All right? We haven't gone anywhere, we haven't done anything, so everybody's empty. And then the first thing that we push onto the stack is our starting vertex. The stack is going to hold all the work that we still need to do, all the vertices that we still need to visit. All right? So I'm going to push onto the stack S. I'll just keep it open, I guess. I'll push the vertex A, because that's what our example is going to be. And then we hit this while loop, and we just keep going as long as S is not empty, and of course we started it out non-empty. So here's what we'll do. While S is not empty, we'll run the body once. So V is S dot pop, so let's pop A off the stack. We just popped A off the stack, now it's gone. All right, what do we do? If that V, which is A right now, if it's not been visited, then we should visit it for whatever our definition of visit is. Maybe we'll print everybody out, but there's a reason you're going through the graph. Do the thing you were meaning to do right now on the vertex. You just found a new one. You're processing the node, maybe printing it out, looking at its stuff or something, and then you're adding it to the visited set. We just visited A, okay? We just visited A. And so I'll add it to the visited set. I'll keep that one open too. There. All right. And then what you do to make sure that you go everywhere else from A, you push all of V's adjacent vertices, call them W, to S. So the very first thing we popped off the stack, the very first thing we discovered was the A node. Right? We just popped it off. We ran it. We ran with it in the body of the while loop. All right. So that's the first thing that got visited was the A node. Okay, and then we push all of its adjacent vertices to the stack. So B, C, and E, we're going to push onto our stack in some order. Doesn't matter. Maybe I'll put them in just left to right order. That's fine. B, C, E. All right, and that means E is at the top of the stack. The order doesn't really matter. It's all going to work out just fine. Okay, so now we have a non-empty stack, and we're done with one iteration of the while loop. We're going to come right back on into it and do it some more. All right. So while S is not empty, we're going to pop it. So we're going to pop that E off the stack, and it's not in the visited set. This is our first time seeing the E, so we're going to have to visit it. So visit E, maybe print it out, do something cool. So we just visited. It's number 2. All right. So it's like from here we went here, kind of. That's the second thing that we noticed. And then, of course, we just visited E. We did something with it, so we'll add it to our visited set. And then we'll push all of its adjacent vertices to S. And so what's adjacent to E? This is a bit wasteful, and you'll see right now, because, well, we have A is adjacent to E, and so is F. But we've already visited A, so it kind of doesn't make sense to push it, but the algorithm's telling us to push it. So we'll push A, and we'll push F, because those are the two things adjacent to the E node. Okay, that's going to be our goal. So now F is at the top of the stack. We're done with another iteration of the loop. So we come right back into it. Stack is, of course, not empty. So let's pop off the top of it, which is the F, and we'll visit it. Maybe we'll print it out, do something cool with it, and then we'll add it to our visited set, of course, and push all of its adjacent vertices. It's the third thing that we saw. We kind of came at it through E. If we wanted to remember that, we could. We push all of its adjacent vertices to S, which are going to be B and E. You see, it's a little wasteful because we've already been to E. And so what's going to happen is, oh man, E is now at the top of the stack. Like, we're done with another iteration. We come back in, we see E, so we pop it off. But E is in the visited set. We just popped E off the stack. Like, we're supposed to go and visit it, but only if we haven't seen it yet. We have seen it. So we just skip that if statement, and we don't add anything new to the stack. We just like get rid of that thing because we've already done it. And now we come right back into the top of the loop with something we haven't seen. So we get the B now. We pop the B off. I think you see where we're going with it. We visit B, adds it to the visited set, and we add all of its adjacent vertices. It's the fourth thing that we noticed through F. We add all of its adjacent vertices to the stack, and so we'll like add A and D and F. So there's a bit of duplication. I think you can maybe think of how you can make this a bit faster, but we'll come back into this loop on the F now. But we've seen F already. F is in our visited set, so get rid of it. D though, D we have not seen. So we're going to go and visit that one. So in the next iteration of the loop, we're going to pop the D off. I hope you see how it's working. Pop the D off, and it's not in the visited set, so let's visit it, do our stuff. Remember that we have visited it so that we don't do that again. It's the fifth thing that we saw. So it's kind of building that little structure. That's how it learned about D through B. And then push all of its adjacent vertices. And that is just B. And so now we're back in the loop, and I'll just do it a bit faster now. I think you get the idea. So B we've seen, go away. A we've seen, go away. A we've seen, go away. C we have not seen, so we're popping that off. It's not in visited, so we're hitting the body of that if statement now. Visit the C, do something cool with it, mark that you saw it, right? Add it to the visited set. It's the fifth thing that we saw, and it was through A. We pushed it through A, but it just took a while to get there. It's because A wanted to search as deep as possible into the tree first. See what it's doing there? That's what depth means, okay? And then push all of its adjacent vertices, which is going to be A and G, bag, and then we're back into the top of the loop. So pop the G off. We have not seen the G yet. Cool. So that means we need to visit it, add it to the visited set. In goes the G. And then it was the sixth thing that we saw, and that will be the final thing. We add all of its adjacent vertices to the stack, so we have a C that's adjacent to G, though we've been there. We're just going to add it because that's what the algorithm tells us to do. And we'll just keep popping it, and notice that everything is in the visited set now. Like we pop the C off, it's already there. Pop the A off, it's already been seen. Pop the B off, already there. And so that is everybody. We have visited everybody. I can like close this off now. The stack is empty. I visited everybody that I can through A, and I went as deep as I could first, and then did the rest. That's kind of what depth first search is all about. And yeah, that's the idea. You could do this recursively with recursive calls to a DFS function, because what is a stack data structure but a very similar thing to your function call stack. So either way works, but I think the explicit stack is helpful for the next algorithm. So that's depth first search. I'd like to teach you about breadth first search. So depth first went as deep as possible. Breadth first is going to go as wide as possible. Search as wide as possible rather than deep. And all you have to do is replace the stack with a queue, like the same algorithm. It all works out. What it's going to do is like stay close to your starting vertex, much more than this algorithm did. Okay? And, oh, I should talk about the running time. So you're going to visit, depth first search is size of V plus size of E time. And you use the plus because you're not sure which one's bigger. Maybe there's a ton of vertices, or maybe there's a ton of edges. You're not sure which one there is more of. And so you just put the plus, and whichever one's the bigger one will win out. But the idea is it's definitely V time because we're going to visit all the vertices in the worst case, and we just did. We have to do constant work at them, most likely, like visiting them. So that's V time. And then we also have to push every edge that we see, like every adjacent thing. We're going to push like the fact that we can go to D, F, or A from B. And so we're essentially looking at every edge and doing something on the stack with every edge. See that? So that's V plus E time, and there's a similar idea with breadth first search. Also V plus E time. Look at what we can change, though. Instead of pushing all of V's adjacent vertices to S, it was a waste because we're just going to pop them off if we've seen them. Let's change that part to push all the unvisited adjacent vertices, all right? So that's going to be the new thing. So this is called BFS, breadth first search. Takes a graph, takes a starting vertex, we'll do A again. And what it's going to do is it's going to go as wide as possible. So like here's our starting vertex. It's going to go like visit these three things first, if those are where you can go. Maybe even some more, I'm not sure. And then from there, it'll go like as deep as possible into each of these. So that's going to be like the search path that it sees. Hopefully that makes a little bit of sense. So it's like going to go here first, then all of these first, then all of these first. If you've seen a breadth first traversal of a tree, it's the same idea. All right? It's going to create essentially a tree for us that looks kind of normal. So all we have to do is take DFS, replace the stack with a queue, and we get breadth first search. Same running time for the same reasons, but let's watch it work. All right? So the visited set starts out empty, of course. We haven't seen anything yet. And now we have a queue, which I will use the capital Q for. Why not? So create an empty queue, and I'll use just a list to talk about a queue. And we're going to push to our queue the starting vertex that we want to visit from. And let's do A again. All right? So, all right, we hit the while loop. While the queue is not empty, we're going to pop the queue. And remember that popping a queue pops off the front. So like we pop the A. I'll keep it here this time. We pop the A, and we haven't seen A yet, so let's visit it. Add it to our visited set, and we'll push all of its unvisited adjacent vertices to the queue, which is quite nice. I guess they're all unvisited at this point, but B, C, and E we're going to push to the queue. B, C, and E. We push, and then we come right back in to the loop. So while the queue's then empty, it's not. Pop off the front. Ooh, that's a B this time. Pop off the B, it's not been visited. So visit it, maybe mark it somehow. We came there from A. Add it to the visited set, push all of its unvisited adjacent vertices to Q. Isn't that nice? So that we're not going to waste time with A. We're going to push the D and F. Isn't that sweet? And then we come back to the start of the loop. But what is going to happen next, because it's a queue, it remembers the first things that we pushed onto it. It's going to go to the C next, not the stuff from B. And so that means it's going to go wide rather than deep. That's the goal of the breadth first search. So it's going to pop off the C. It's the third thing that we saw through A, and it's not been visited, so we'll mark it as visited. And then we'll add all of the unvisited adjacent things to the queue, which is going to be the G. Just the G. But we still are working on everybody else's stuff before that, because in a queue, you pop stuff from the front, not the back. Isn't that sweet? And so then the fourth thing that we notice is going to be our E. That's going to be the next thing at the top of this loop. When we pop from the front of the queue, we pop the E and visit it. It has not been visited yet. So we see our E, and we saw it through A. It's the fourth thing that we see. We visited it, push all of its unvisited adjacent vertices to Q, which will be the F. It's going to be seen later, but we don't know that yet. So we push it because it hasn't been visited. And so we're back in the loop now. Now it's time for D. Right? I'll go a bit faster now. So D has not been visited, so we'll visit it. D, we saw it through B. It's the fifth thing that we see. And yeah, we push all of its unvisited adjacent vertices to the Q. There are none. So we just keep going. And then, again, we're back at the top of the loop. Pop it off, pop off the F. We have not seen F, so we're going to visit it. It was through B that we saw it. It was through B that we got here, because we pushed everybody when we added it to our visited set. So we add the F. We've just seen it. We saw it through B. It is the sixth thing, though, that we saw. See kind of the order? It's like doing all this one, then everything that's one distance away, then everything that's two distance away from A. That's what a breadth first search is all about. Then we push all the unvisited adjacent vertices to F, which are none. B and E have already been seen. And so we just keep on going. Pop the Q, we see the G, we saw that through C. It's the seventh thing that we saw. We visit it, of course. Add it to our visited set. Oops. Make a smaller circle, I guess. And then we add our G. There it goes. And push all of its adjacent vertices that have not yet been visited. There are none. So we just keep on trucking. And we're back in the loop. Pop the Q. The F has been visited, so we skip everything, and now the queue is empty. We are now done visiting everybody, and look at the way in which we visited everything. It's all in, like, everything 0 distance away from A, everything 1 distance away from A, everything 2 distance away from A. It drew that tree that looks kind of normal. Depth first search went as deep as it could the first time. That's what the stack gives you versus the queue. It went like this. It drew this kind of weird looking tree. That one and that one. See that? See the differences? So that's depth first versus breadth first. It's just replace a stack with a queue, and everything starts looking different. You have your reasons for doing each of these, definitely, though. They do take the same amount of time, but sometimes you want a breadth first search, and sometimes you want a depth first search. Okay? So, let's keep going. I have the coolest algorithm saved for last. It's going to take us a few slides to get through, though. So let me show it to you, and we'll talk about it. All right? It's called Dijkstra's shortest paths algorithm. And this one is when you have a graph with weighted edges. You want to find the minimum path from a starting vertex like A or something to everywhere. You want to find the minimum way to get to G. There's only one way. The minimum way to get to E is just go straight here rather than like take this roundabout route. This Dijkstra's shortest paths algorithm is going to teach us how to move around, how to get to the fastest place. All right. So essentially, it is this algorithm again, and we're just changing out. We're swapping out the data structure one last time for a priority queue. Remember what that is? That has a heap as the underlying data structure. And so we're going to pop off the minimum thing because we want to find the minimum path, the shortest path with the minimum weights. that's all we have to do, just swap it out with a priority queue. We're also going to have to hold on to some extra information to know like how to move around, like what is the path. We'll save that in a certain way. I'll show you later. But the goal of Dijkstra's algorithm is that you take a starting vertex, like A, and then what it's going to do, it's going to find the shortest path from that starting vertex to every other vertex. So it is a little bit of a waste if you're just trying to look for how to get from A to D the fastest, for example. But it's good when you want to know how to get everywhere, all right? So it is essentially, let's see here, it's this amount of time, because take the v plus e from before, but now to pop from a priority queue rather than a stack or a normal queue, it's no longer constant time. It is logarithmic time in the number of things, which could be potentially the number of nodes in the graph. So it's this amount of time to run when you swap it out with a priority queue, because every action is logarithmic to pop from it and to push to it. But you can actually do better than that with a fancier data structure called a Fibonacci heap, which that is the topic of a advanced algorithms class at a four-year college. So let's not go there, but it's still a pretty good time. And it was invented by Edsger Dijkstra, and he's just so cool. Here's his picture. No longer alive, unfortunately, but he is a legend. He actually, I am related to him by PhD advisors, which is funny. He's my PhD advisors, PhD advisors, PhD advisors, PhD advisors, PhD advisor. So I'm like 6 PhD advisors out from him, which is funny. But this is just one of the coolest algorithms that you'll learn, and hopefully it's a little bit intuitive. But if anything seems fuzzy, here's a cool link to a very fun tutorial with pretty pictures that you could read through to get a better understanding of Dijkstra. It's actually going to teach you a more advanced algorithm called A-star, which is going to stop at a goal rather than just find the minimum path to everywhere. But it's good to read through it. All right, so do that if you'd like. Here is the algorithm, though. All right, so imagine we have this graph, but it has weights now. What do we do? How do we find the shortest path? We need to save that, right? It's no longer just a visited set. It's like, how do we get from A to some place, to G, from using the shortest possible path? All right, so we need some more data to hold on to. So we have a visited set as usual. We're going to have 2 new maps, though, in addition to our priority queue. All right, it's called a distance map, dist map, and a pred map. All right, so the dist map is just the graph itself. It's like you can ask for what is the distance to A, the shortest distance to A. It's going to store the shortest distance from your starting vertex to a given vertex. So like, what's the shortest distance to the A node? And so we're going to essentially read that off the graph at the start, but we're going to compute the shortest paths and save them in dist and maybe update them as necessary. And then we have a pred map. Pred stands for predecessor. It's going to map nodes to where we came from. So it's like going to build up this idea, these arrows, these edges that I was drawing, like that's not built anywhere, that's not saved anywhere. We're going to save that with a pred map. It's telling us where we came from, okay? And so it's like the predecessor of E was C. That's where we came from. So like here's the path that it's like saving onto. Sorry, backwards. A, C, E. If that's the shortest path from A to E, for example, the pred map would be taking that backwards and remembering it backwards. So it's like, to get to E, we came from C. It's the predecessor of it, okay? That's the idea. And so, yeah, we're going to start off some empty things, empty maps, empty dist, pred, and then we'll have an empty priority queue. All right, again, we have some starting vertex that we want to find the shortest paths of everything, to everything from there. And we start off with an empty min priority queue. So we're going to pop off the minimum thing first. All right. And we are going to push an interesting data structure. All right. We're not going to push nodes. We're going to push nodes with some knowledge of where we came from, and also the distance that we think it took us to get there. Okay. So it's like a big struct that you that you push into this queue. It's the starting vertex with where we came from, prev set to the starting vertex, like How did we get from A? We came from A. It's like you draw a little loop at the start. It's just a silly default value. Don't worry too much about that. That's just how you know when you got to the start. Silly default value. And then you save the distance. You always save the distance that you think it took to get to this place, and how far does it take to get, how much work do you need to, how much distance do you need to travel? That's the right phrase. How much distance do you need to travel to get from the starting vertex to the starting vertex? You don't have to travel anywhere, so just 0. So that's the kind of data that you're pushing. Starting vertex, where you came from to get here, how you noticed it, and then also the distance that you think it's going to take to get there, okay? That may be the minimum distance. We'll see. We'll save it in the dist map. All right? So that's the goal, and that's the starting thing. And then forever, we're going to do a very similar idea. We're going to pop from the priority queue, but we have 3 things stored inside of every piece of the priority queue. We have the node itself, the vertex, where we came from to get there, and the distance to there from where we came from. And so we're going to pop. And we're prioritizing in our priority queue based on this distance. That's the number. This minimum thing is going to be the one popped off first. It's going to take the prev and the starting vertex along for the ride. I promise this will make more sense when I give you an example. But we're going to pop all 3 of these things off. And it's going to be the node with the min distance. That's what we save. All right, I have an example that's going to be worked through on the next slide. And here's the algorithm. It's very similar to the other one. If that v that we just popped off is not invisited, then this must be the shortest path. If you think about it long enough, this must have been the shortest way to get to v, because it had the min distance, right? And we haven't seen it yet. So we'll save that the distance to v must have been the shortest path. The distance to v from the starting vertex must have been whatever this dist was that we stored, that we saved in the node, saved in the struct, I guess, that we added to the priority queue. And then we save that, all right, in the shortest path, we came from this place to get to v. So the predecessor of v in the shortest path is prev. And then we add every adjacent vertex. So for every adjacent vertex that has not been visited, because if it has been visited, you can prove that we've already found the shortest path to there. We don't have to look at it again. So for every adjacent vertex that is not in the visited set, as usual, we're going to add it to the priority queue in this way. We're going to add that node with, remembering that we came here from v. That was the v that's the edge that we followed from v to w to get there. And then also the distance that we think it's going to take if we at least go through our v. The distance to this w through v is going to be the distance to v itself from the starting point plus the weight along the edge from v to w. So like if it was b and d, if that was v and w, then we're going to add the weight 5 to the weight like 8 that we got. That was the shortest path to b. Okay? That is the idea. All right. So that's a lot of words. It's a lot of things. I want to draw it all for you now, and I think that will help make it all make sense. Here it is. So Dijkstra, G, starting vertex. Here is our graph. Let's pretend that we're starting at D, and we want to find the shortest paths from D to everybody. So that's like our starting vertex from D to everywhere. Okay? That's our goal. So I'm going to walk through this, and hopefully it'll all make sense when I show it to you. So the visited set starts empty. The priority queue starts empty. Dist and pred, they're maps. They start empty. Empty, empty, empty. Nothing in them yet. Okay? And the first thing that we add to our starting at the empty priority queue is we're going to add, it's like 3 things. Starting vertex, and the distance of 0. So it's like, we're going to add the D. What was its previous node in the graph? It's just a dummy value when you're at the start. It's like, all right, we came from D itself or something. And then the distance from D, from the starting vertex to this node is, of course, 0 because we just started there. So this is the next node, and this is the prev part, and this is the dist part. Let me draw that a bit better. This is prev, this is dist. Okay, so with that, let's run the loop. While the priority queue is not empty, let's pop off the thing with the minimum distance in it, and that is, of course, going to be this thing. It's the only thing there, distance 0. It's the D node. We just popped off the D node. And what do we do? It's not been visited, so okay, we mark that it's been visited, so we never see it again. This must be the shortest path from D to itself. So we're going to add it to the visited set. And then we're going to remember that the shortest path distance to V is the one that we saved along. It was the 0. All right, so the shortest path distance to V in the dist map, we're going to mark that as D maps to its distance of 0. And then the predecessor, where do we come from to get to this V that we found, to our D? Well, we came from D itself. It's just a dummy value at the start. It's just, you loop it around. This will make more sense when we add real things, but we map that D, we came from D. It's a silly way of doing things. And then now, for each adjacent vertex, W, such that W is not invisited, which is just the B, right? We have not seen B. That's the only place that we could go right now. What we do is we add a new triple to our priority queue. We're going to add, we could go to B from the V, which was our D. We can go to B from D, and the distance to get there that we think, if we went through D at least, is going to be the distance to V, which is 0, the one that we saved, plus the weight to get from there to B, which is 5. So 0 plus 5 is 5. So we could get from B to D with a distance 5 path. There's a way. Okay? That's what it's saving. And that's the only thing that we add. And so that's the end of one iteration of the loop. We come back because PQ is still not empty. It has this one thing in it. We pop off the min thing, and the thing with the min distance, here it is. It looks like the shortest path from D to B is going to have length 5. All right? When we pop something off, we just found its shortest path. That's the only way to get there. It's the fastest way by default. All right? You can prove that. So we just popped off B, D, and 5. And D has not been visited, so we'll add it to the B has not been visited. We'll add it to our visited set, and we will save its shortest path distance. It was 5. It's that thing that we saved. So the shortest path to B from our starting vertex is going to be 5. It's a length 5 path, weight 5 path. How did we get there? We got there through D. So the pred of B is D, because the previous thing along the path is D itself. And then for each of V's adjacent vertices that have not been visited, so skip D because we've seen it already. We just saw B though. Add it to our visited set, I guess. And then we're going to add F and A. Those are the adjacent things, all right? So if we add those to the priority queue. So we add that we could go to, that's how you do it. We could go to F from B with the distance. What is it? It's going to be the distance to B itself from the starting vertex of the 5 plus the weight along that edge. So to get to F through B, it's 3 plus however many it took to get from the start to B, which was 5, so 8. So we have FB 8 if we went through this route. And then also we could get to A from B with a weight, well, we have 5 plus 8. So that's going to be 13. That's one way to get to A, all right? And that's going to end our iteration of the loop. And so now we have 2 things in our priority queue ready to be popped off potentially. So we come back to the start. We're going to pop off the thing with a min distance, which is going to be this one. We're going to skip the A and go straight to F, because that must be the next thing. That's the shortest path, all right? We just found the shortest path to F now. We pop this off. It must be length 8, all right? So we have not yet seen F. So we're going to add it to our visited set, and we'll mark that the distance to it is going to be 8. The distance to F from the starting vertex is 8. That's the shortest path distance. And how do we get there? We got there through B. We saved that. So F, the previous predecessor of F in the shortest path of length 8 is B. And that's how you can generate it later. And then you're going to go and add every adjacent thing to F that has not yet been visited. So we've seen B, of course. So let's add. We just visited F. I'll circle it. We need to add E. We can go to E through F. So we'll add that. We could go to E through F with a length, let's see, length of F was 8. That's the path length to get there. distance 8 from the start, plus the weight to go along the edge from F to E, which is 9. So we can go from E to F with a length 17 path if we wanted to. Maybe that's not the shortest though, like maybe that's faster. We'll find that later, potentially. Okay, so that is what we add, and then we're going to pop off always the shortest thing. So it looks like we come back to the loop, we started off, and we notice that we could go to A. That's the shortest distance. It's always we're popping off the min thing in the priority queue, so we're popping this off. We just found the shortest path to A. All right, so A has not been visited. Add it to the visited set. The distance to A is the 13 that we saved here. That's the shortest path distance from the starting vertex. And then now, how do we get there? We got there through B. So the predecessor of A is B. And now, we just visited it. For all the adjacent vertices that we have not yet seen, we're going to add them to the priority queue, and like the fact that we can go there through A. Sorry, it's hard to draw a circle apparently. Okay, so through A, we could go to B, we've seen though. We can go to C or E. Those are the unvisited things. So from A, this is just me doing all this part. From A, we could go to C, from A, with a distance, let's see. Well, what was the distance to A? It was 13, plus the 6, that makes 19. We can go to C through A and that would be a 19th length path, 19 weight path. We could also go to E through through A, sorry. Go to E through A from A with a length, 13 plus 7, so that's a length 20 path. That may or may not be the shortest path. It's always the priority queue is going to give us the minimum thing. It's going to give us the right answer. All right. So those are the things that we add to our priority queue, and I believe we are ready for another round. So we're going to pop up the thing with a min distance, which looks like it's the E to F. The rest of those are too big. So the E to the F, we pop off, and that means we just found the shortest path to E from the start. So E has not been visited. We're going to add it to our visited set. And we have found the shortest path to it. It's going to be of length 17. So it's visited. I'll circle it to remember that. The distance to there, the shortest path distance to E, is going to be what we saved, the 17. And where did we come from to get there? We came through F. So the predecessor of E in the shortest path is going to be F. Excuse me. And I'll draw this backwards for us when we're done. But now, all right, add all of the adjacent things through E. Are you ready? So what could we add? Well, we've seen A. Skip that. But we could go through F. Oh no, we've seen F. Darn, so we can't add that either. So there's nothing to add for E. We're done. We come back into our loop, and we pop off the shortest path thing. Are you ready? So it looks like between these two, the 19 is smaller. So that's the C. To get to C, that is the shortest path. C has not been visited. Add it to our visited set. Its shortest distance is going to be 19. So we'll save that. The distance to C is 19 from the start, and how we got there was through A. So the predecessor in the shortest path is going to be the A vertex, and we add everything from C that we have not yet visited, so it looks like it's the G. We'll add that to our priority queue. We'll push it. So we can get to G through C with a length, well, C was 19, plus the 1 to get from C to G, that's a length 20 path. And that's what we add to our priority queue, and we come back to the loop. And now, these are both length distance 20, so we could pop off either one, it doesn't matter. Let's pop off the E through A one, and notice that we've already seen A. We have a better way to get to E. It was a length 17 path. We've already done that. And so if we visited E already, and we just skip it. We just skip it. This was a worse path. And that's how it always finds the best one. You just give it all the options, and it will find the minimum one first. That's the goal of a priority queue. Isn't that nice? And then finally, we only have one last thing to pop off. That's the G, 2G through C of length 20. That has not yet been seen. So we're going to add our G to our visited set. And we're going to mark that, all right, we can get to G, and the shortest path from G or 2G from the starting vertex is length 20, and we got there through C. All right? And we're going to push, we just visited it, we're going to push all of its adjacent, unvisited vertices to our priority queue, and there are none. It's just C, and we've already seen C. So now we have traversed everywhere that we could from D, the starting vertex. Now we have successfully computed the shortest path to everywhere. Isn't that cool? So you can just read it off. So for example, there are a couple ways to get to F, right? Here's a silly example. There's this way, the fast way, and then there's like this roundabout way. Dijkstra is going to tell us the fastest way. And you can read it off. So the shortest path distance from D to F is going to be, just look up F in our dist map. It's going to be of length 8, and then if you're wondering how you got there, you just start at F. Like, how did we get to F from D? Well, follow the pred map. Where did we come from along the shortest path to F? Well, we came from B. All right, so it must have looked like this, the path, and then we go to B. Like, what was the shortest path to B from the starting vertex? We look up B as the key of the pred map, and it looks like we came from D. And then you can look up D, and you notice that like that maps to itself. That must have been the starting vertex. Now I'm done, and now we've just constructed the shortest path. Do you see that? That's how you can do it. So that must be the shortest path, and you can do the same for everybody else. Like, how did we get to E, for example? Was it this way or was it this way? You can find out by the predecessor map. E came from F, so it must have been this way. You see that? And you can just follow it, and you can generate the path with the pred map. And if you just needed to know the distance, the dist map gives it to you. So technically, if you didn't need to construct the path later, you don't need the pred map. You just need the distances. You can just use the dist map. The dist map is absolutely necessary because that tells us things. Pred, though, is only useful if you want to reconstruct the path that you formed. All right? And so that is the Dijkstra's shortest path algorithm. It is a mouthful. It's hard to speak precisely when I talked about it. I had to check my words every time, but we got through it. Now the priority queue is empty. The algorithm is complete. We have all the distances, all the shortest path distances to from the start to everywhere, and then we have the paths themselves if you'd like to follow the pred map backwards. Isn't that so cool? And so you can construct like the paths that you took to get from the starting vertex if you want to build that pred map. You can do that here too, to construct the actual, like, here is this breadth first kind of tree thing. Here is this depth first tree thing. Yeah, I think that should make a little bit of sense now. But that is Dijkstra's. It is the fanciest algorithm. It's so cool, and I hope you see its value. So that is where I want to stop here. Only 6 slides today, right? But so much content in them. That is the end of our graphs slides. We'll talk about them a little bit more in the trees slides, which are next, but that will be for next lecture. I will see you there.